We've seen that it's possible to make epoxides by first forming a bromohydride and then doing an intramolecular Williamson ether synthesis. To recap, and using a bicyclic structure so that there will be some facial selectivity, if we were to take this molecule, which can be drawn in boat form, with the bridge coming like this, and in this case, the bottom face is the sterically more hindered because you have these two axial hydrogens on the back carbons interfering with the bottom face versus just one hydrogen. In the previous example, we had a CH3 here, and that larger CH3 group hinders the top face. But here, these two hydrogens cause more steric hindrance on the bottom, so the bottom face is more hindered. Which means an electrophile should be attacked by the top face of the system. And we know that if we react this with bromine and water, and in the second step, react this with KOH, we can first form the bromohydride and then deprotonate the oxygen and cause a three-membered ring to form. So let's look at the mechanism. For review, the pi bond will attack bromine, kicking out bromide, and that bromonium ion will form on the top face. Pushing the methyl group and hydrogen down. And then water will come and attack at the more substituted end from the bottom face. Thus leaving the bromine on the top at the less substituted end and pushing the methyl group back up. So the oxonium ion is on the bottom face. And then we'll deprotonate that. So that our OH group is down here in the axial position. And let me redraw that so that it looks more like it's in the axial position. And our bromine is in the equatorial position. So our electrophile ended up at the less substituted end of the double bond, and it ended up at the less sterically hindered face. And bromine was the electrophile. So regiochemistry says that it's at the less substituted end. And stereoselectivity at the less hindered face. Now when we treat this with hydroxide, we're going to go a simple acid-base reaction to deprotonate and form an alkoxide ion. And the alkoxide ion is perfectly situated on the opposite face from the bromine, so that nice intramolecular SN2. Which is the Williams-City synthesis. So the final product of this reaction will have an epoxide on the bottom face of the molecule. The more hindered bottom face away from the bridging methylene group. Which is great if what you want is the epoxide on the more hindered bottom face. But what if you want the epoxide on the less hindered top face? What if we wanted to make the other stereoisomer where the epoxide plates up on the same side of the molecule as the bridging methylene group? Well, it turns out that's possible, and in fact, the mechanism for formation of the epoxide on the top face using the appropriate reagent also goes through a 3-membered ring intermediate, which means that it undergoes a very similar pathway to this top reaction with the electrophilic bromine. The difference being that it will be a single step converted or concerted reaction where the initial product will already be the neutral epoxide, as opposed to this multi-step reaction that we have with the stable bromohydride intermediate, which you see here prior to the adding of the sodium hydroxide. The reagent for this epoxidation reaction which is an oxidation, has the acronym mCPBA, which stands for meta-chloroperoxybenzoic acid. It's a peroxy acid, so we have that oxygen-oxygen bond, and the chlorine is in the free position, which is the meta position of an aromatic ring. The 2 position is called ortho, the 3 position is meta, the 4 position is para, so the chlorine is here. The electrophilic oxygen is this one. This oxygen has a partial positive charge on it because of the electron withdrawing effect of the carbonyl, pulling electron density away from that oxygen. So you'll actually have a dipole here that puts a partial positive on the oxygen that's connected to hydrogen. So the pipeline is going to attack that electrophilic oxygen. And the product will be the epoxide on the top face, same side as the methylene bridge, and it all happens in one step. Solvent for this reaction is usually dichloromethane, but sometimes it's ether. And when you use ether, it exploits the fact that the other product, which is meta-chlorobenzoic acid, or 3-chlorobenzoic acid, is significantly less soluble in ether than is the peroxy acid, which means that it precipitates out and facilitates purification. Usually it's not difficult to purify though, because this product is acidic and can be washed out with sodium bicarbonate solution. Because it's a single step concerted reaction, when we show the mechanism, we want to show the structure of the transition state. I'm going to draw the electrophilic oxygen on the top face there because I know that's where it's going to end up. And I'm going to draw the remainder of the molecule so that I have a rough 5-membered ring between the hydrogen, the 3 oxygens, and the carbon. And it'll become apparent why in a second. Pi bond attacks the electrophilic oxygen. A pair of the electrons from the electrophilic oxygen comes in to form the second carbon-oxygen bond, so we have the 3-membered ring forming the epoxides, and it kicks out a leaving group, in this case, the leaving group of benzoic acid. But because of the way we've arranged this, we can show the flow of the electrons to the final product. This pair of electrons that is the oxygen-oxygen bond will actually become the carbonyl pi bond of the product. The pair of electrons that's here is going to end up on oxygen because this oxygen is going to pull that hydrogen off, returning a pair of electrons to the oxygen so that it will still have 2 lone pairs. This lone pair that remains untouched and a new lone pair from there. So we have 2 different cyclic systems going on. Where we have the 3-membered ring forming here through the movement of 2 pairs of electrons, the pi bond attacking the oxygen and a lone pair on the oxygen attacking the tertiary carbon. And we also have a cyclic system of electron motion happening up here in this 5-membered ring, where we have the oxygen-oxygen and oxygen-hydrogen bonds breaking, and we have a new carbonyl and oxygen-hydrogen bond forming. So there's a lot of electron motion going on, which makes drawing the transition state somewhat complex. So in the transition state, we have started to break this pi bond. And simultaneously, we have started to form a bond to this oxygen from each of the 2 carbons in the 3-membered ring. I'm going to move that oxygen a little bit so that those 2 bonds will be distinct. So in this part of the cycle, we're breaking a pi bond and forming 2 carbon-oxygen sigma bonds. In this part of the cycle, we're breaking the oxygen-oxygen single bond, forming a carbon-oxygen pi bond, breaking a carbon-oxygen pi bond, forming an oxygen-hydrogen sigma bond, and breaking an oxygen-hydrogen sigma bond. So in all, we're forming 4 new bonds and breaking 4 old bonds. So there are 8 bonds involved in the transition state that are either breaking or forming. So 8 partial bonds in the transition state. Think of it as a 5-membered ring cycle where we're breaking 3 bonds and forming 2 new ones, and a 3-membered ring cycle where we're breaking 1 bond and forming 2 new bonds. So we're breaking a carbon-carbon pi bond and a carbon-oxygen pi bond, an oxygen-oxygen single bond, which we know is quite weak, and an oxygen-hydrogen single bond. We're forming another oxygen-hydrogen single bond, so those two kind of cancel each other out energetically. We're forming a carbon-oxygen pi bond, so those 2 bonds kind of cancel each other out. So what we're in essence doing is forming 2 new carbon-oxygen single bonds at the expense of a weak oxygen-oxygen single bond in the peroxide and a weak carbon-carbon pi bond. So even though the 3-membered ring is strained, it's energetically downhill to form 2 stronger carbon-oxygen single bonds and break a weak oxygen-oxygen single bond and a weak carbon-carbon pi bond. The product, if we draw it, leaving all the atoms kind of in place, then ends up looking just like what I drew, with the hydrogens in, right? And we have our carboxylic acid having switched to which oxygen is the acidic oxygen, or the hydroxyl group that precipitates out of solution or is washed out with dilute bicarbonate because of the acidic hydrogen, and we end up with our epoxide. So it's very simple to write the reaction on a note card. It's simply meta-chloroperoxybenzoic acid, which looks like this, in dichloromethane or ether, and we get our product and the 3-chlorobenzoic acid. It's kind of a lasso. This pi bond lassos this oxygen out to form the epoxide and spits out the benzoic acid product. 3-membered ring intermediate, right? 3-membered ring transition state, rather, no intermediate to this because it's inserted. And this looks just like the bromine, where the electrophilic bromine is being attacked by the pi bond and a pair of electrons is coming in to form the second sigma bond and kicking out a leaving group. The difference, of course, is this time the oxygen has another hydrogen attached to it, so it needs to go through the other 5-membered ring to get that hydrogen off. Pretty straightforward, and it's the last example of our reactions that go through these 3-membered ring intermediate to